guys, you got to watch those two problems. It's the guys who aren't here, who were not here when I did those two problems. Let's see what resume share. I've never used that one before. Oh, that's not what I wanted. New share. The PowerPoint. Oh man, it took me all the way out, didn't it? Why won't it come back? Oh, this is such a pain in the neck. PowerPoint is a Microsoft product, and it is such a pain. Minimize that. Wow, it took me all the way out of Zoom. New share, PowerPoint. Come on. I don't know what's going on here. I think it's completely lost its mind. I can't get it to do anything. Let me try another new share here. This is absolutely nuts. Okay, return to meeting. Can you not do that? Okay. New share. PowerPoint. I don't know what's going on here, folks. I think what I'm going to have to do here is, your internet is unstable. That's what the problem is. Let me get rid of one thing here. I don't think this should be bothering, but let me get rid of it. Okay. No, I don't want to do that. Okay. Now, my internet looks good. Why will this not work? I don't know. Okay, let me try something else. Let me try going to the whiteboard. Ah, there's the whiteboard. Maybe it's good that I went there. Okay, folks, for those who just logged in to see what we did tonight, I forgot to turn on the Screencast-O-Matic, so you missed the first few problems we did as homework. We haven't covered any new material tonight, but the homework questions were excellent. The problem is I've already gone over them. Sorry, I can't go back and redo it because that would take too much time. For any of you who have just tuned in, if you notice the time is now 6:06, we've been going since 5:06 or 7, something like that, because I was in a meeting with the deans and department chairs and inputters. They were talking about summer and fall schedules, and the meeting just flew by, and I didn't realize because my time wasn't showing when the Zoom was up, and when I got out of the meeting, I saw it was after 5 o'clock, and I did panic. Okay, so anyway, we didn't get started until an hour ago, but now we've been working only homework exercises since then. So let me get, this will not, it will not open. Okay. So what I'm going to do, I'm going to go down here. Okay. All right. I'm going to try one other. Okay. Let me do from current slide. Okay. Now we'll do a new share and see if it works this time. Or this time. There we go. Wow. Took forever to get back here. Okay. Any more questions before we get on to new material? Yay or nay? Okay. Excellent questions, by the way, folks. All right. Where we are then, starting tonight, with only 30 minutes left or less, is talking about friction. And if you, how many still don't have books? Let me know. I need to know. No penalty or anything. I just need to know. Does anyone not have a book yet? Okay. Glad you said something. Well, I will try to write this stuff down, and I think maybe it might be easier for you to read if I type it in. So I'm going back to the whiteboard and put these 3 points about friction. Anyone need this problem up there a little bit longer? No. Okay. So I'm going to clear the drawings and then go to text and type in 3 points about friction. Okay, first, sort of a definition. Friction is a force that always acts parallel to the surface in contact and opposite to the direction of motion. Okay, that's the first statement about friction. Friction is a force measured in newtons, by the way, or pounds. Okay, can't quite get it all in there, but it's most of it. It's a force that always is parallel to the surface. Now, if this book were the surface here, the friction, and you're trying to slide something, say my calculator, across the book, it doesn't slide easily. So I'm pushing this way, friction's it's always parallel to the surface and in the opposite direction of the motion. Okay, if I were pulling this way, then my pull is this way, friction is opposite but parallel to the surface. So it all has to do with the surface. Now I'm going to do something else. I'm going to tilt the surface, okay? And right now friction's holding that calculator in place because it's sort of a rubberized surface here. So it's holding it in place. So even though the weight is pulling down, the friction is parallel to the surface. Not parallel to the ground, parallel to the surface, opposing the pull of gravity down the plane. Okay, if I tilt it this way, now friction is opposite to the direction of the pull. Okay, so friction is a force, always acts parallel to the surface, whether the surface is flat or at an angle, and opposite in the direction of the motion if there were motion, or the force that's trying to create it. Okay, now let's go back for just for an instant here. And okay, go to the next slide here, and here we see an effort force here trying to move the crate in this direction, but because there's friction between the crate and the surface, the frictional force is always parallel to the surface. This just happens to be flat surface here, a horizontal surface. It's always exactly opposite. Here's a bigger crate, 2 crates piled on top of each other, so there's more friction. If you remember the illustration before of the microscopic irregularities between the 2 surfaces, when this peak here is down in this groove, it's going to be really hard to move that. And if you put more weight on it, it's even harder to move it. Okay, so that's what we're seeing here. It takes too many slides. A greater effort force to try to move it, and still the friction force is greater. Okay, now will this move? Not if it's stationary to begin with, but once this effort force exceeds the maximum friction force, then it'll move. Okay, and then something else happens. The friction force usually reduces, and that's what we're going to get at next. Okay, so let's go back to our whiteboard again. Okay, that was the first topic, and for some reason it's lost the text. Here's the second. Static friction is greater than kinetic friction. Now, I like to put is usually greater than. This book just says greater than. I like to put usually greater than because we're going to see a table in the book that basically contradicts this, okay? But that's the second. Now, what do we mean by those? Okay, let's go back to our picture here, our slide. Okay. Why is this? Okay. Now, like I said before, if this was stationary, okay? Now, let me do this with my calculator on my book again, okay? Now, I'm going to push, believe it or not, on that calculator. I am pushing. Not very hard, but I am pushing. So there is a force in this direction, but it's exactly equaled by the force in that direction, which is the frictional force. Why do I know it's equal? Because that calculator isn't moving, okay? That's called static friction, the friction that opposes motion, okay? Now, I'm going to push a little bit harder, okay? And finally, I get it to move, okay? Once it's moving, now there's still friction there, but this friction is called kinetic friction because that's the friction of motion. And if we go back here, remember when this is pushing here, if this is exactly equal to that, there probably is no motion. But if this exceeds this, then you finally get it to move where your friction force actually reduces it. And this is what this is showing. You see, when this is in motion, here it's just pushing, but this isn't moving. When this does start moving, that's why the line's here, the friction force actually gets less. This is static friction here. This is kinetic friction here. Kinetic friction, it's no longer down in the grooves. Now it's riding along the top, and it's easier to keep it moving. And that's why if you've ever been pushing on something like a car or something trying to get it to move and it's so hard to push, but then when it finally moves you almost fall down because the kinetic friction is less than the static friction generally, okay? So that's the second point. Static friction is generally greater than kinetic friction. The stationary friction is usually, the force due to friction is greater than the kinetic friction. And the third point, okay, for some reason the text disappears every time I change. So pick it up again. The third point is friction increases as the force between the surfaces increases. Okay, and that's what we pointed out before. I pointed out before. Okay, unless the friction increases as the force between the surfaces increases. What that means, going back to our figure here, come on, resume slideshow. It didn't do it. There we go. If this force between the surfaces, the weight here pressing down on here, this is less than this one because this is twice as much weight pushing down. That means you're going to have to, of course, push with a greater or pull with a greater force here in order to overcome the greater force here. So the frictional force is proportional to what we call, and this is a sort of a new term here, and this is what they're going to do next, the normal force. Now remember what normal force was? Let's go back a few more slides. Here it is. whatever the weight is of the earth pulling down on this brick, as long as that brick's not bowing the table or breaking the table, that means the table has to be pushing upward with an equal but opposite force because the brick's not moving. So the net force has to be 0. Well, for the net force to be 0, the normal force from the table is equal to the weight force pulling by gravity. Well, over here, because you have twice as much weight force here, or assuming these have the same weight, this is a greater normal force upward here than you have here. So that leads to the next, and this is your formula now. Good to pay attention to the formulas. They are your friends. Okay, I'm going to go back to the text. Oh, I probably don't want the text now. Okay, because this has a subscript and I can't type a subscript. So let me get my pad back. And here's what we just said. Whoa, goodness gracious. When I don't want it to write, it writes. When I want it to write, of course it doesn't. Okay. All right. Now, your frictional force. Remember, your weight force is F sub W. Your frictional force is F sub F. Capital F for force, little f for friction. Friction force is equal to, and here's a funny little symbol. That symbol is a mu. It's from the Greek alphabet. It's like our letter M in the Greek alphabet is written that way. Okay, I'll tell you what it is in a minute, and that's equal to mu times the normal force. Now, I just showed you what the normal force was in that other thing. That is the force that the surface is pushing up on the object, which is usually exactly equal to the weight of the object coming down. Well, why didn't they put weight there? Well, if you're on an angle like this, weight would be straight down toward the center of the earth, whereas normal force is like that. So it's more precise to talk about the normal force. Okay, so this is the frictional force. And this is called the coefficient of friction. Now remember, back to this point up here, there's two types of friction. If I can get my pen to show up, there it is. There's static friction and there's kinetic friction. So quite often I will put either an S after this or an F after that. I mean K after that for static friction or kinetic friction. Okay? Because they are slightly different. Static friction is usually greater than kinetic friction, so the mu sub S is usually greater than mu sub K. So I will write that here. Mu sub S is usually greater than, I'm going to put greater than or equal to. That's supposed to be an arrow there, but it's not a very pretty arrow. Mu sub F. I mean mu sub K. I don't know why I keep saying F. Mu sub K. Kinetic friction. And this, of course, is the normal force. Normal force. Okay. Now this coefficient of friction is a ratio between the two forces. If you divided both sides by, say, the normal force, you would get force due to friction divided by the normal force is equal to mu. Now if you think about it, and that could be mu sub S or mu sub K, whichever, whether it's moving or stationary, okay? This is measured in newtons, that's measured in newtons. That means this has no units whatsoever, just a pure number. If this was in pounds, that's in pounds, no number whatsoever. Mu would be mu whether you're in the SI unit or the US customary units, because the units cancel out. It's the same mu. Now, I don't want to write all these down, but I will hold them up for those who don't have a book, on page 132 are some of these coefficients of friction. They're steel on steel. Notice for static friction, I can't read that because it's backwards, 0.58, but kinetic friction 0.20. Yeah, static friction's a lot more than kinetic friction. Steel on steel lubricated gets almost frictionless. In fact, they're the same there, 0.13 and 0.13. It doesn't matter whether it's static or kinetic, they're both very, very low. Glass on glass, 0.95 static, 0.40 kinetic. Okay, less than half again. Hardwood on hardwood, that'd be oak on oak or something like that, 0.40 or 0.25. Okay, now for some reason here, for steel on concrete, they don't list the static friction. Why, I do not know. But for kinetic friction, they list 0.30. That's a mystery to me. Okay? I have a feeling someone just didn't do it right. Aluminum on aluminum, they're 1.9 for static friction. They don't list anything for kinetic friction. And I do have a clue on why that's the case. And here's what it is. Okay? Aluminum is a very soft metal. Okay? I'm going to go back a couple slides. Oh no, I can't do that. I need to go back here. Okay? Resume slideshow. I'm going to go back a slide. Okay. Aluminum is a very soft metal. So basically we have a piece of aluminum up here and a piece of aluminum down here. And since it's a fairly soft metal, this point here is going, when it's down in this groove and this one's down in that groove, and you try to push it, it's going to dig into the metal, to the aluminum here. That one's going to dig in here. They actually get harder to move with kinetic than they do with static. So that's one case where they don't even list the kinetic friction because it's hard to measure. Okay. Whoa, where am I going here? Okay. Well, I don't have to be on that. Okay. Let's go back to this. I don't know if y'all can read them here. The next is rubber on dry concrete. Now, where would you ever have rubber on dry concrete? Your tires on the road, exactly. And look at what it is. It's 2.0 static friction and 1.0 kinetic friction. Now, what does that mean to you? When you're driving your car, you want that to be, now we haven't mentioned this, but that's a type of friction called rolling friction. You want that to be static friction. You do not want the tire to be skidding across the concrete. If you are, you're spinning your wheels. Okay? And if you're doing that, you have no control of your car. So you want that to always be static friction, because once you start sliding, you have less control. You can't control the car. And that then leads to rubber on wet concrete. And notice what those numbers are. 1.5 for static, 0.97 for kinetic. Now the kinetic didn't decrease by much, but it did decrease, but the static also decreased. And what that gets to mean, it's a lot, on wet concrete, it's a lot easier to lose control of your car because it slides. The water takes the place of some of those grooves down here, fills those up, and now it lubricates. Basically, that's what it's doing. The water lubricates, and these slide more easily. So you lose that control that you had of your car. And if that was ice, you're even in worse shape, way worse shape. Aluminum on wet snow, I don't know why they said, oh, I think I do too. Aluminum on wet snow, look at that one. 0.4 static, 0.02 kinetic. Okay? Now, when might you ever have aluminum on wet snow? I wouldn't, but maybe you would. Sledding or skiing. Exactly. If you have aluminum sled or aluminum skis, that's exactly what you have. And you know you have to push it a little, get it going, but once it's going, it goes. Okay? And then steel on Teflon, that's just really, really low. Anyway, Teflon is a great lubricating surface. For instance, your cooking ware. They used to be Teflon, now they have Califon or something like that is a newer one that just makes it non-stick. Everything slides pretty easily. All right. Then they have a little activity, how to find mu. You can read through that if you want to. It's not really important for the course. How am I doing on time? See, once I'm in Zoom, I don't have my... Whoa! Say that again? Yeah, 29 after, yeah. So we don't have time to do the activity, but once you get your book, you can try it if you want to. It's not very important. To reduce kinetic friction, use smoother surfaces. Okay, what does that mean? Maybe sand the surface or fill in the grooves in a surface or something like that. Number two, and this is even better, use lubrication to provide a thin film between the surfaces. Number three, like you just saw, use Teflon to greatly reduce friction between the surfaces when an oil lubricant is not desirable. Like electric motors. You don't want oil in electric motors because there may be arcing and sparking that could catch fire. And substitute rolling friction if you ever can for sliding friction. Rolling friction is the resistance that occurs when an object such as a tire wheel or a tire rolls on a surface, and then you want to have the static friction, not the sliding friction. Now, when you in your tire they have ball bearings, that's rolling friction, and that's really low friction, especially if they're well lubricated. All right, we made it right up into example 1 because we got such a late start, which was my fault. I lost track of time at the dean's meeting. It's her fault, you know. So that's where I'll tell whoever takes over the course, that's where you'll begin next time. Okay? I'm sorry we didn't get any new material covered, but y'all had great questions from the former material. And after that one example, then you're going to have the problems. If you want to try some of these, you can. Any of the odds, 1 through 7 or 9 through 15. But you don't have to do them until you don't have to do them, period. But until we do the example. That wouldn't quite be too fair. Now, another thing that came up, and I don't know who's going to teach the course and what they're going to do about it. But the last time I taught this course was last summer. And last summer they didn't put this requirement on us. I sent you an announcement that explained starting last fall, they decided that virtual courses like this one should be done almost the same way that online courses are. Well, to me, they're very, very different, and I find it ridiculous to put this on you. But what they do with online courses, of course, you usually don't have times like this that you're able to be here and see me and I can tell you're there and stuff. What it does, the instructor puts out the assignment the first of the week, and at the end of the week, if it's not turned in, you're not counted present for the week. So what they said, we ought to do the same thing. So they wanted us to make at least one assignment a week. So what I did with my classes last term, I didn't teach this one, but my others, whatever the homework was, I said, turn in at least one problem. Okay? Now, I don't grade them. They don't count points. It's just to indicate that you're doing your work, which I think is a good thing to do. But if you're having trouble with some of those are the ones I really want to see, and then maybe I can say, oh, okay, here's what you're doing wrong. And I don't think any of you sent me any this week. Well, I didn't look. I didn't look at I completely forgot. Okay, was it sent via email or on that site in the on week 3? No, no, you can send anything you want. Well, you wait and see who your instructor is and see how he wants it sent, or if he doesn't even want them whatsoever. I was thinking if you did send them through Blackboard, I didn't check it on Blackboard because I kept thinking, so he's going to show up and be able to teach the course this week. So I blew that one. But yeah, if you send it late today, I was in that meeting and didn't get to see it. So, but check with whoever your instructor is, Dr. McBool or Dr. Bryant, either one, and one of them will be with you next week. If they don't say anything, just do whatever they tell you. They'll have to sort of start, not completely over, but tell you how they're going to run the course. Probably would be differently from what I'm running it, but whatever. Now, I did put on your weekly activities. I thought we were going to finish 5.4 tonight, and I also thought we'd do 5.5, but because I was late and then we had questions, we didn't get to do any problems. So I'm going to move the test 1 off of this week, and probably it'll show up next week, but that will be up to the instructor, whoever it turns out to be. Because next week I'm going to be on the beach in Florida. No, no, no. I'll be retired, but I'll still be right. What's that? Well, thank you so much. Uh, I got a gift today. They've been sending me all this stuff about the summer schedule and fall schedule and said they're coming up really soon. They sent them out, so I spent most of the today, and that's one reason I didn't check email before, because I thought we would be working on those schedules in today's meeting. So I was already planning which courses to drop and doing all that kind of stuff, and then the meeting just was yak 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 yak, but it went on forever. But when I said, well, I'm not going to be here for much longer, they said, oh, we've already taken your name off. I thought, why am I in the meeting then? But they've already taken my name off, so I don't have to turn in anything for that. So I'm almost feeling like I'm retired already, but I've still got miles to go before I sleep, but I'll try to get it done. But I've thoroughly enjoyed having you as students for 3 weeks only, and I'm so sorry that I did miss the first part of tonight, and then I forgot to turn on Screencast-O-Matic. But I will save what I've done so far, put it out there on YouTube videos. It'll probably get loaded either sometime later tonight or sometime. It'll definitely be loaded by tomorrow morning, so I'll get it posted on the playlist sometime tomorrow morning. So if you run into any of the students who were trying to get into the class, let them know I was just late because I was in a meeting and literally did not know it had gotten that late, because just like now, I can't see a time on the screen. I didn't even think to look at my watch because it didn't seem like any time had passed, and suddenly it was 5 o'clock. So take care. Have a great term. I wish you the best. Thank you. Bye-bye. Thank you. You too. Bye-bye.